Let's talk about descriptive statistics. More specifically, we're going to talk about frequency tables. We're going to talk about measures of central tendency, as well as measures of spread or variability. Descriptive statistics are numbers and graphs that are used to summarize the characteristics of a sample. So whenever we go out, we collect the sample, measure individuals on different variables. We want to be able to create graphs and calculate values so that we can share that information. That calculated or resulting from our sample make up descriptive statistics. The type of graphs and numbers that we use will lead us to differing types of statistics and graphs. And so, just as a quick review, remember when we have qualitative data, those are data that are measured on the nominal and ordinal levels. They're going to have different graphs and statistics or numbers compared to our quantitative data, which are measured on either the interval or ratio scale. No matter the type of data and the level of measurement, we can always create frequency tables. Frequency tables are tables that are used to summarize the number of times a value or an interval of values appear within our data set. The main name of these tables are frequencies, and a frequency is the number of times a value appears in our data set. So we can create frequency tables for any type of variable, but depending on the type of variable, we're going to have to do some different we're going to have to consider some different things. Before we get to creating some frequency tables, I'm going to show another sample data set. This sample data set has more variables than what we're going to focus on in this example here. But I have this data set that I downloaded from the South Carolina childcare.org website. And it basically contains data on active child care centers in South Carolina. This data set has a sample size, which we're going to use the variable n to represent sample size. So there are a total of 2,479 active child care centers in South Carolina. And we have these variables on that first row of that data set. We're going to focus on some of these. The first variable is the ID variable, and each child care center is represented on a different row. So we have these differing IDs. IDs are usually not of interest to us while we're doing data analysis, but it does allow us to go back and check some things if we need to. But each child care center, so each observation represents a child care center, and each has a different ID. We have the variable permit type, which is the type of regulation a child care center has. We have the facility type as another variable, which is the type of facility. Some of them are in homes, some of them are child care centers, so on and so forth. We have the county where the child care center is located. We have a variable called ABC level. Each state has their internally created quality rating system. And in South Carolina, the quality rating improvement system, that's the word or term. In South Carolina, it's called ABC quality. And there are multiple levels. So a provider may be rated as an A+ childcare center or an A. We have B+ as well as B. And then the lowest level is a C level provider. And then you're also going to see some other values in this variable. For instance, NR means that provider is not participating in that quality rating improvement system. That means they're not rated. And then you may see the variable P in this data set. P means that their rating is pending, meaning they've gone out and been evaluated, but their final score has not been finalized yet. And then the other variable that we may be interested in is the capacity, and this is the licensing capacity. So each permit or facility type correlates to a maximum capacity. Childcare centers can be as big as possible, but those that are in a home, a group home, or a family home may have a smaller capacity that they can legally operate within. And so we have this capacity variable that just gives the licensing capacity. It's usually based off of the facility type as well as the the square footage and the number of rooms that they have in their buildings. All right. But I want to just identify, just for us at this time, the level of measurement of each of these variables. As you can see, I'm not using numbers in columns B, C, and D. And it's because these are all nominal variables. But the ABC quality level, there is some order that's inherent in that variable. So that's an example of an ordinal variable. And then the capacity variable, it is numerical and the numbers have meaning. It's the capacity, the number of children that they're legally allowed to operate. And that is a ratio variable because it has a zero, a true zero. The other variables we're not going to worry about in this data set. They are not nominal because they're a true false. So let's go and look at the frequency table for an example of making a frequency table for a nominal, and the same will work for an ordinal variable. All you have to do, because these are categorical variables, is look at or find all of the categories. So for instance, I'm looking at the permit type variable here. So my first column is headed permit type, indicating my variable, and I'm going to have a column here that says frequency. All right. Well, I have to have all of the variables of that permit type variable. And if I were to go through that whole data set, I'm going to see that there are 4 permit types. And so all I do to create the frequency table is count up the number of childcare centers, the number of rows that has approvals. If I look in that data set, it's going to be 215. I go to the next permit type, which is license. There were 1,340 of those, so on and so forth, right? So this is a frequency table. It kind of gives you an idea of how many observations have each of the values of that variable. Now, notice that there are 2,479 observations in this data set. And if I add up these frequencies, I get there. That means we have no missing data. But because this is not like a whole normal number that we can kind of visualize and like a standard number, I don't know another way to put it. Sometimes we don't want to look at the frequency or the count to compare categories. We want to look at like the proportion or the percentage. And so the proportion of times a value appears in a data set, that is known as our relative frequency. And so to calculate that proportion, all we have to do is take each of those frequencies, which I'm going to, in a formula, use the variable F to represent frequency. So I can go to approval, take that 215 divided by the 2,479, which is the total sample size, and I'm going to get the relative frequency of approval permit types in that data set. All right. And if I were to multiply that by 100, I would get a percentage. And so just as I said, to get the relative frequency, which is can be another column in my frequency table, and do that for all of my variables, I get kind of a standardized way of seeing our data instead of looking at these numbers here. Now notice here, if I add up these proportions, these relative frequencies, they should add up to 1. And if you ever get into a space where they don't add up to 1, that means that there may be, doesn't mean that there's an issue or an error, but due to rounding, I round these to 2 places after that decimal. Sometimes when you do that, you may not get to 1. You may get to 0.99 or 1.01. It happens ever so often. So that's a frequency table for ordinal and nominal data. You can do the same thing. When it comes to quantitative data, those interval and ratio variables, you got to kind of think a little differently. Because a variable is numerical, they can take on any number of values. There can be an infinite number of values that these variables can take on. And so I'm going to think about a frequency table differently depending on the number of different values that I see in that table. So if I don't have a lot of different numbering numbers of values, say let's say I look at my data set and my quantitative variable only takes on 12 different values, then I'm going to create my frequency table almost in the same way that I just did with those nominal and ordinal variables. But I'm going to have numbers in that first column instead of terms or categories. But if I have a lot of differing values in that variable, then I'm probably not going to want a table in order to visualize the distribution of my variable. I'm probably going to use a graph, and that'll give me a better depiction of what my data look like. Now, one of the most popular graphs to use for quantitative variables, whether they're interval or ratio, will be something like a histogram. We're going to talk about histograms in the next video, but that's one of those graphs that we'll use. One thing about histograms is that they use a specific type of frequency table where we divide our data into equal intervals. So many intervals are each with equal length. We call those intervals of equal length or with classes. And we basically count the number of observations that fall within each of those classes. And that is our frequency. And so I'm going to go back to that data set. We already talked about it pretty well. But the capacity, remember, that's the maximum number of children that a provider, a childcare provider, can legally serve. And so we have that column highlighted here. As you can see, we have a lot of differing values of this capacity variable, right? This is a discrete ratio variable that has a lot of values. So again, I should create a histogram, but I want to show you some of the behind the scenes frequency tables that those histograms kind of base their graphs off of. And so, just as I said before, we're going to take the values of that quantitative variable and we're going to break it up into classes. And so, I think the smallest capacity in my data set was 1, and the largest capacity was in the 600s. And so, what I did was I just decided to divide my classes, my variable into classes whose length is about 49 to 50, right? Well, 50. 1 to 50 is 50. All right. And so I basically broke it up into these classes. So my first class goes from 1 to 50. My next class, there should not be any overlap. So I'm going to go to 51 to 100, then 101 to 150. Notice I don't have any overlap there. And this is a discrete variable, right? We're not going to have any values between 50 and 51. So I'm good to go there. So these are all of my classes of equal width. Then I'm going to go to my data set and count up the number of observations that have a value within that interval, within that class. So there are 1,117 individual childcare centers that had a capacity between 1 and 50, and these are the rest. Now notice here, if a class doesn't have any observations, I'm still going to put it in my table, but I may have some zeros within that class, a frequency of 0. Notice here, we had a sample size of 2479, and not all of those childcare centers actually had a capacity listed. And so sometimes creating these tables like this will allow you to see if you have any missing data. I clearly have missing data because my total, if I add up all these frequencies, is not equal to the total sample size. All right. So these were some notes here to be sure that the classes do not overlap. It is easy to do this when you have discrete variables. You have to think about this a little more when you have continuous variables. We're not really going to be creating we're not going to create any frequency tables in this class. We'll have the computer do it for us. But you'll start to see things like in math or pre-algebra when you talked about intervals of numbers, and you use things like parentheses and brackets to say whether a value will be included or not included based off of the endpoints of that interval. You have to think about that a little bit more when you have continuous variables. But we almost never make these frequency tables by hand, but they are used to construct histograms, and I wanted to show you an example of that. So that's a table, and of course, these frequency tables can be used with any type of variable. Now let's talk about some of the other numbers that we may have. These are measures of central tendency. Measures of central tendency are numbers that represent the central value or a typical value in our data set. And these are probably the most known statistics when it comes to people thinking about statistics. For instance, thinking about your mean, your median, and your mode. All right. The mode of a data set is the most frequent value or values in your data set. So, which values occur the most? It may be one value that occurs the most, or there may be multiple values that occur the most. So, that's your mode. That's considered a measure of central tendency. Probably the most popular measure of central tendency is your mean. Now, I'm going to try to stick to the notation that's in your textbook. Do note that we're not going to focus heavily on notation, and this notation is very simplified in your textbook. So it's going to be simplified in these lectures. All right. If you go online or go in and reference some other sources, you're going to see some Greek letters and all this other stuff. I'm just going to keep it simple and keep it consistent with your textbook. All right. So the mean, we're going to use a capital M or an X bar. That's more aligned with what other textbooks uses in the field. But that is your arithmetic mean or average. That just means to add up all the values and divide by your sample size. Now, there's a formula here, and I'm going to introduce this notation here to add up all of the values X in your data set. So let's say I have all of those capacities, right? They're all each represented by the variable X here. So there was a provider that had a capacity of 99. So one of the X values in my data set is 99. Another provider may have a capacity of 17. That's another X value. So I would just add up all those values. That's what this sigma, this Greek capital sigma, means, to add up all of your observations X and then divide by n, your sample size, or the number of values that you added up. The median is another measure of central tendency. It's the value that lies in the middle of an ordered data set. And so in order to calculate the median, you need to order your data set, and then you just pick out the middle number. Now, it depends on whether you have an even or an odd number of observations in your sample size. If your sample size is odd, you're going to have one number in the middle. That value is your median. But if your sample size is even, then you have two middle numbers. And in order to get that median, you're going to have to take the mean or average of those two middle observations. So add them together, divide by 2. So I'm going to look at this example, a couple of examples of these measures of central tendency. The mode aligns with you can use it with your qualitative type variables. They're more interesting to report the mode. And so here I have permit type. If I want to know what the mode of that variable is, just look at the category of highest frequency, right? So the permit type that occurs with highest frequency is licensed childcare centers, right? That is our mode, license. I have another data set here, and this is a much smaller data set because I want to calculate my median here by hand. In this data set, I have the number of glasses of juice individuals in a sample drank per week. I do want to make a note here that sometimes, to simplify our data set, we can group some of these observations together. So instead of having 11, there were 0 individuals that had drank between 11 and 34 glasses of juice in that week, right? So instead of having 11 through 34 on separate lines, all with the value of 0, we just group them together to consolidate our table, which is perfectly fine. But if you count all of these or add up all of the frequencies here, you're going to see that you have a total sample size of 48. There was one observation in that data set that drank 1 glass of juice that week. There were 2 that drank 2 glasses of juice that week. And there were 4 that drank 3, so on and so forth. So if I'm going to find my median by hand, I have my numbers in order, but I've got to make sure that I have the correct frequency. So I can list all of my observations. This is a little tedious here. There's 1. There are 2 2s, because the frequency is 2 for the value 2. There are 4 3s in this data set, so I have to have 3 listed 4 times. And then I can write all of the rest of my data in order from least to greatest like this. Now, If I want to find the median, I have all of my values of my variable in order. I know that there's an even number. So the observation in the 24th and the 25th position, divide that by 2, right? Get to the 24th. So the observation in between the 24th and the 25th position would make up my median. Those two there, if I take the average of those, I get 7. So the median of this data set is 7. Now, if this was 47, I would just take the middle number, and that would be my median. But I have an even number. Now I'm going to look at the glasses of water individuals drank in a week. Well, it doesn't say in a week, so I don't want to assume that. So this is just glasses of water. This is the frequency of our observations here. And I have 15 observations. And I want to calculate the mean. Well, for me to calculate the mean, I'm going to use that formula. I have M, or X bar, equals the sum of all of my observations X divided by N. So I'm going to write out all of my observations, add them together, divide it by 15, which is the total sample size, and I'm going to see that I get a mean of 4.33. Now, there are other means. We look at the arithmetic mean as a measure of central tendency. In education, we use the weighted mean a lot, especially in relation to grades. And so we'll talk about weighted mean. By definition, it is the mean of a data set whose entries have varying weights. So for instance, W is going to be the value of what we're calling a weight, and X are our observations. If I want to calculate a weighted mean, I'll do the sum of the product of each X with its weight. So it's the sum of the product of X times W, and I divide that by the sum of the weights. Let's look at this example. It says you're taking a class in which your grade is determined from 5 sources: 50% from your test mean, 15% from your midterm, 20% from your final, 10% from a lab, and 5% from homework. The scores that you end up having is 86 for your test mean, 96 for your midterm, 82 for the final, 98 for the lab, and 100 for the homework. We want to find the weighted mean of the scores, and if 90 is the minimum average for an A, did the person with these scores get an A? Well, I've organized my data into this chart here, and in order for me to get the weighted mean, I'm going to have the sum of the product of X and W, the scores and the weights, divided by the sum of the weights. And one thing about weights, especially in terms of an example like this, we need these weights to add up to 100% so that you'll have a whole grade, right? And so our weights here add up to 1. And so that's going to be our denominator. And then I need for my numerator the product of X and W. So I'm going to have to take that 86 and multiply it by that 0.5. Add to that the 96 times the 0.15, so on and so forth. We get these values here. We add those values together. That gives us our numerator of this formula for our weighted mean. And so we put those values together. 88.6 divided by 1 is 88.6. And that value is less than 90. And so the score would not be an A. So those are our measures of central tendency. The weighted mean is sort of some extra stuff, but definitely the mode, the median, and the mean are measures of central tendency. Now let's switch gears and go to measures of variability. All right. These are numbers that measure how much observations within a data set differ from one another. So not only do we need the measure of the central or typical value, but how spread out are the values in that data set, right? And so one measure of tendency, of variability is the range, all right? The range is basically the difference between the minimum and the maximum variables in that data set, or values in that data set. So the difference between the min and max values or observations. Another measure of variability is called your standard deviation, and a lot of times we abbreviate that with SD. It is a measure of how much in general, your scores differ with respect to the mean. So it's not just how different they are, but in terms of the mean, how far out are they spread. This one has a massive formula. This symbol here, if you recall, is your square root symbol. And under that square root, we have a sum of x minus m. Remember, m, we can use that for your mean, your sample mean. So I'm going to take the observation, subtract the sample mean, square that, and I'm going to add up a bunch of those values. That is what that numerator under that square root represents. Once I have that sum, I divide it by my sample size minus 1. Then I take the square root, and that's going to give me my standard deviation. This is something that we report a lot, and so we can use this formula because it is reported a lot. Something that's not reported as often in a lot of statistical applications is known as your variance. The variance is just the square of the standard deviation. The square means to raise it to the exponent 2 or the second power. So if I take a square root and raise the entire square root to the second power, it cancels that square root and we're just left with the stuff in the middle. All right. So these are some measures of variability. We're going to get to some others, but we'll focus on this one in this lecture here. Let's look at some examples where we calculate range and at least standard deviation and talk about why we maybe rarely report the variance and more often report the standard deviation. So here I have a very small data set that contains the number of years of experience of 6 PE teachers. Let's calculate the range, variance, and the standard deviation. Remember, the range is the max minus the min. Our maximum is 17. Our min is 1. So our range is 16 years. Now, for me personally, that range, it is valuable to know, but a lot of times I'd like to know the actual minimum and maximum values. So sometimes I'll report my range by just using the minimum and maximum values. But the range is truly just one year, or one value, which is 16 years. But a lot of times we may see it reported this way. The number of years of experience of PE teachers in this sample ranges from 1 to 17 years. That gives me a lot of information. Now, if I had 2 groups of PE teachers and I wanted to know which group was more widespread, then comparing the single number will be valuable. But reporting to the public, especially having this written this way, is very, very helpful. Now remember, let's go to our standard deviation and our variance. The formula for both of them actually include our sample mean, which means we're going to have to calculate the sample mean in order to get the standard deviation and the variance. And so that, once again, you add up those values, divide by the number of values, and in this case, we get a sample mean of 8. Now, this standard deviation is a measure of basically how far our observations are from the mean or relative to the mean. We already know that our mean is 8. And let's talk about this word deviation here. A lot of times, the term is standard deviation, but deviation means how much does something differ from something else, right? And that word differ means that we're going to use a difference, all right? That is why this formula in the middle has a difference or a subtraction. So this difference is the same thing as a deviation. So one of the things that we're going to do to start calculating standard deviation is calculating those differences. So I'm going to take each score or each number of years, that observation X, and subtract from it the mean 8. So 7 minus 8, of course, is -1. 12 minus 8 is 4. Notice this value is negative, this value is positive. And I can continue on calculating these deviations. So all of these X minus M's are deviations. Now, I want to calculate how far off observations are from the mean on average. Well, in order to calculate an average, all you have to do is add them all up and divide by the number of observations that you just added up. So let's try to just do this. Let's take all of these deviations, add them together, and divide by the number of observations we have. Well, if I add up all of these deviations here, all of the x minus m's, I get 0. So thinking about adding up all the observations and dividing by the number of observations you added up to get a standard deviation, or on average how far observations are from the mean, you're always going to get a 0 here. That is why instead of just adding those up, we're going to square them, right? We have some negative and positive values. They end up canceling each other out. So we're going to go one step further to square each of those deviations so that we don't get things canceling out anymore and end up with a sum that always equals 0. This is why we go and square and think about our variance. So let's square all of these values. And when we do that, we get these values here. And of course, when we add those all together, we're going to get a non-zero value because the square of any real number is always positive. Excuse me. And so now that I have the sum of x minus m squared, I want to divide it by n minus 1. And when I do that, well, we had 6 observations. So 6 minus 1 is 5 in that denominator. My numerator is that sum. I get 36.8. That value there is my variance. And I want to talk about why we have variance and standard deviation. Well, we have to think about units. This x is measured in number of years, right? So the 7 years, 12 years of experience, 17, so on and so forth. When I subtract by the mean, I'm still having years, but I may have positive and negative values. So all of these deviations are still years. When I go to the squared deviations, now I'm no longer in years, I am in squared years, or square years. So this numerator here is in square years, and I'm just dividing it by a count, which is why this 36.8 here is in years squared, or square years. This is why we rarely report variance in descriptive statistics. It's because they're not in the same units as the original variable. They're in squared units, right? And so in order to get it in the same units as our original variable, years of experience, we take the square root, and hence we get the standard deviation. So that's the square root of that 184 over 5, which if I round that to 2 decimal places, I get 6.07. That is going to be in years. And we can interpret this as the typical number of years observations deviate from the mean is 6.07 years. Or I can say on average, observations are about 6.07 years from that mean of 8. All right. So that is our standard deviation. While we go through that squaring and taking the square root and all of that, we'll actually rarely use these formulas here, but I wanted to go over the formulas so that you'll know what and why these things are calculated the way that they are. So that sums up all of the descriptive statistics in terms of the numbers, or most of the numbers that we're going to use. We will see some others in our next video, or the one after that. But I want to talk about how we choose the appropriate descriptive statistics. If we have nominal variables, we're going to use frequencies, and you can always change your frequencies to relative frequencies, which can be written as percentages, and we'll report the modes, right? The same thing happens with ordinal variables, but your textbook did point out that you could sometimes report a median for your ordinal variables. I don't see that a lot in practice because these aren't necessarily always numerical, but that sometimes you will see people report ordinal variables, the median of ordinal variables. And then for your interval and ratio variables, it's going to depend on how your variables are distributed. Now, I'm going to use a term here that we're going to get to later before the end of this week. But if your interval and ratio variables are normally distributed, we're going to want to report the mean and the standard deviation. And if they're not normally distributed, we're going to report the median and the minimum and maximum values, or the range, right? Normally distributed refers to the shape of the distribution and some other characteristics of that distribution. There's more to come on this. And so I'll wrap this video up here now. Right now we have our tables as well as some statistical indices, or numbers that we can use to describe data. Next, we'll start looking at actual graphs that can help us describe data. And so I'll see you in the next video.